Hi, I'm Nigel Allinson. I'm a professor at the University of Lincoln, and I'd like to say something about our vision and how it compares to those cameras in our smartphones as part of our contribution to British Science Week this year. And it's very interesting to think, as an engineer, of the similarities between what has evolved through nature and what we've managed to do as engineers. The human eye is one of the most complex objects that we know. And it's not just the eye, because it's connected to that big computer at the back, the brain. It's amazing how much information passes through it. We can understand the world, we can move through it, we can recognize objects, we can miss objects. But let's first think how we actually see light. And nearly all our light comes from the sun. Okay, at night we can turn on the light, but basically it's photons. Photons are massless quantities of energy which make up light. And if we look at the light that's given off from the sun, and here's a diagram of the energy given off at different wavelengths from the sun, shown in that orange shape there, and compare that to a perfect black body with a temperature of 5,900 degrees Kelvin. And once that sunlight's passed through the atmosphere, and due to the absorption, due to water and other molecules in the air, there's some dips. But the part we see, shown here with this coloured spectrum, the visible spectrum, we can see one that it matches very closely to the maximum power output, energy output of the sun. So how do our photons cause us to see? So here's an atom. It's an atom of silicon. At the centre is a nucleus with its protons and neutrons, and around it are the electrons in their orbits. And when a photon comes in, which has a certain amount of energy, there's enough energy to dislodge one of those electrons and make it free to form an electric current. And the energy we need to release that electron, is a few electron volts. For red light, it's about 2 electron volts, and for blue light, it's about 3 electron volts. An electron volt is the energy we have to give to one electron to raise it through 1 volt. It's a very small amount of energy. Our 60-watt light bulb is equivalent to about 70 million electron volts. So let's look at the human eye. There's a cross-section on the left, and at the front there's the lens and the pupil and the muscles that control the lens so we can focus on objects close and far away. And at the back we have the retina. And here's a very simplified picture of what the retina looks like. At the back of the retina are 2 main types of photoreceptors. There are others, but they're the rods and the cones, and we'll explore those in more detail in a few moments. And they connect together through a number of neurons, the bipolar cells, the ganglion cells, and then to nerve fibres that pass out of the eye through the optic nerve. And you can also see it right at the back of the retina. There's something called the retinal pigment epithelium, the RPE. This serves a lot of important functions. It protects the eyeball, it provides nutrients to the cells, and it also absorbs light. So any light that gets past the rods and the cones, we don't want it bouncing around inside your retina. You get some very strange effects. The other thing to notice is, if I'm going to make something that's very sensitive to light, why do I make the photosensitive bits at the back, behind all the neural tissues? I'm going to lose sensitivity. There's a good reason for that. Because I'm walking through the park and I'm walking past a set of railings. And what you see is I get these strange bands passing through. It's called aliasing. And if we didn't low pass filter take out the highest spatial information in the image, then we would see all the time these sort of aliasing patterns. If we look more closely at the retina, we can see at the fovea, if you like, the centre of the eye, It's densely packed with cones, about 2 microns across. They have colour vision, high spatial acuity, we can see fine detail, and there's 3 types of cones. We call them blue, green and red. There's about 6 million of these cones, that's all. And then as we move away from the fovea, the density of them really drops away. And what we get are rods. And the rods are very sensitive to light at low levels. They're not colour sensitive. And even though they look much smaller, they can't see really fine detail. This is because a number of these rod cells are connected to one neuron to amplify the light, but we lose the ability to see fine detail. And in our cones, we have these 3 quite broad bands of sensitivity. The short wavelength, the blue, of which there's only about 7% of these in the retina. And then the 2 quite broad ones, we call them the green and the red, which are quite broad and fairly close together. But even so, we can sense maybe up to 1 million colours, different shades of colour. Well, most of us can. I can't, because I'm colourblind. And colour blindness occurs because the different pigments for the red and the green cones are not as good as they should be. They're more broad. And the coding for that is on the X chromosome. And I've only got 1 X chromosome and a Y chromosome because I'm male. Females have 2 X chromosomes. So if there's a dysfunctional X chromosome, the good chromosome in females takes over. So that's why 8% of men are colourblind, but less than 0.5% of women. Now here's an experiment you can try at home, and it gives you a very good idea of what you actually see. So the subject here is looking at her right thumb, and on her other thumb is a piece of paper with a pattern on it. I've shown the pattern above at the top, blue triangle with the word dog in it. And she's going to move that hand and tell the guy when she can see different things.
Color, shape, or text of the object. Ready?
Yep.
Okay, go ahead.
Okay, it's in motion.
See motion? What about this area? Don't look away, go really slow too.
Oh, I see color.
Okay, do you know what the color is?
Blue.
All right.
Shape.
Shape, what's the shape?
Triangle.
Okay, and let me know when you see the text. And don't look away. I mean, don't look, yeah.
Nope, I see it now.
Right, about there. You're almost right on top of your thumb there. Were you surprised at what you got for your answer there?
Yes. Well, I was surprised that I couldn't see it until it was right in
the field of view.
So when we look at the world and see a complex scene like this in the supermarket, all the fine details are not seen at one time. They're in our heads. We actually see in fine detail very little at one time, but we can still find the pocket of cornflakes. So before I move on to our smartphone, let's just think of whether we've got the most complex eyes in the world. This is the mantis shrimp. It has 2 eyes on independent stalks that can move independently. We have 3 different kinds of colour sensors. It has up to 16. We have 2 pupils, 1 in each eye. It has 6. It can see polarized light. It can also change the wavelengths it can see in some of its colour receptors depending on its environment. So here's our smartphone. And smartphone cameras have come on a great deal. Not only do you see here 2 cameras, but 3, but 4, but 5. Let's concentrate on the main camera lens, the ones that's going to show you the detailed pictures. But how do we detect light in our silicon devices? This is a silicon photodiode. Silicon is a mainstay of all microelectronics, and this is a diode. So we've got at the top a piece of silicon which has been doped to make it have more holes in it, more electrons in it, and at the bottom it's been doped to have more holes. I'll explain the difference with holes and electrons in a moment. So our photons come in, they generate enough light to excite an electron and make it free, and that leaves behind a space where an electron could be, and we call it a hole. It's not a new elementary particle, it's just an absence of an electron. And because there's an electric field, we pull the electron and hole apart so they don't recombine, and we produce a current. Luckily, the spectral response of silicon covers our own visual spectrum and some more into the infrared, which is why all cameras have to have a filter to cut out that infrared photons, otherwise our pictures would look rather strange colours. But if you connected together just an array of photodiodes, you wouldn't get a very good imager. So what you have to do is to put a transistor or two in there. These are called active pixel sensors, or sometimes CMOS imagers. CMOS stands for complementary metal oxide silicon. And here you can see that in each picture element we have 3 transistors. There's a photodiode. This is connected to a buffer amplifier to isolate that photodiode from the rest of the circuitry. We can select the output of that photodiode, the charges generated with another switch, the row select. And also, once we've done that, we have to put back the voltage on the photodiode again, which is the purpose of the reset switch. Now, CMOS imagers come in many shapes and sizes, and we're after really in smart cameras with very small ones. But here's a very large one. This is one we developed at the University of Lincoln, and on the left is a complete silicon wafer. It's 8 inches across, 200 millimeters, and you can see the large square. It's about 13 centimeters square, and that is one active pixel sensor. This was developed for medical imaging purposes, and at the time was the largest imager built in the world. So where did our smartphones start from? Well, it started on the 11th of June 1997, when Philip Kahn rigged his camera to his phone and was able to take this picture of his newly born daughter and send it to his friends for them to see. About 2,000, I think. And that was the beginning. And I do recommend that you search for Birth of the Camera Phone Subconscious Films, because there's a wonderful 4-minute video of how Philip took all his trouble to take this picture of his newly born daughter. The first commercial phone was issued in November 2000 in Japan and had a camera with 350,000 pixels. Now it's estimated over 57,000 pictures are taken on smartphones every second. That's 1.5 trillion per year. So smartphone cameras got cleverer and cleverer, and they got bigger and bigger. And this started the great pixel wars. So here are 4 popular high-end smartphones at the moment. The Samsung Galaxy S23, 200 megapixels in its main camera. The Google Pixel 7 Pro, 50 megapixels. The Apple iPhone 14 Pro, 48 megapixels. The Samsung Galaxy Z, 108 megapixels. Which one would you choose? Just remember that more pixels mean small pixels, mean less light capture, mean noisier images. Now, to get colour, we have to put over the top of each of our picture elements a fine mosaic of coloured filters called Bayer filters. And on our smaller devices, we just have one colour above each picture element. 2 green, 1 red, 1 blue, etc. 2 green because we are most sensitive to green light. But when we go up to these 100 megapixel cameras, we actually have 9 pixels in a little cluster that are green or 9 that are red. So suddenly our 100 megapixel camera is nearer 10. And then There are other things that reduce the fine detail. If we shine a very fine spot of light through a lens, it will come out blurred. This can't help it, it's just the diffraction of light. So the practical final image of any smartphone camera is about 12 megapixels. Sorry. And this is what these pixels look like when they're on a wafer. So the light comes in from above, then we have an array of little lenses, micro lenses, we can see in the image there, to concentrate more light down this tunnel. This tunnel is going to have a light shield to stop light getting to bits of the silicon we don't want it to. Then we're all going to have all the circuitry, the metal wires, the aluminium wires that connect part of the chip together. And then at the bottom of this deep well, we have the photodiode. And it's very difficult to get light to travel effectively down these deep wells. And this reminds you a little bit of what insects have. They have compound eyes. Don't have a simple eye like us with one lens and then a retina. They have lots and lots of lenses, and at the bottom of each lens there's a photoreceptor. This is a picture of a dragonfly, which is about 24,000 of these individual lenses. So if we had to have the same compound eyes but have the same visual acuity, the ability to see fine detail as this dragonfly, it's estimated that our compound eyes would be about 1 meter across. So we get round some of these problems by what the Americans call backside illuminated sensors. We like to call them rear illuminated. And here we turn things over. Silicon wafer is usually about 3/4 of a millimeter thick, but we thin it down, and now the first thing that incoming light sees is a photodiode, and all the circuitry is on the other side. This is how we can have night photography, low-level light photography, and most smartphone cameras now have rear illuminated sensors. Let's just think what happens to these signals. So here's the eye, and all that information passes out through the optic nerve to that very large computer at the other end, the human brain. And the bandwidth, the number of bits of information that are sent from the eye to the brain, are about 8 megabits per second. Compare that to our camera, that's about 500 times more. And then in our computer, in our smartphone, the rest of the smartphone, that's when we process the image, compress it so we can transmit it, etc. So our retina does lots of processing. My camera does very little. So just how powerful is the human visual system? So I just want to end on an example to show this. Now it's normally thought that it takes about 100 milliseconds for us to see or respond to anything. It's called the response time. It's the same time it takes to press a button, light a light, anything. So this is going to show some very high-speed flashing images. So if you feel that you're affected by seeing high-speed flashing images, please look away now. So that was about 60 images per second. And you saw every one of them. You can't describe them in detail, but you recognized what they were. And if I was to say, is this image was in this set, you'd be able to tell me. So we can recognize a lot about the world, not in finest detail, but the main points, in about 10 milliseconds. That's pretty impressive. And we've got a long way to go, if you like, in our artificial engineering world. So thanks very much for watching. I hope you found it interesting, times amusing, and thank you very much. Goodbye.